Hello, welcome to this topic on voltage regulation and power factor. At the end of this topic, you will be able to define voltage regulation, define diversity factor, explain the importance of voltage regulation, describe maximum voltage regulation in distribution line, explain the methods to bring voltage regulation within permissible limits, define power factor, explain reasons for low power factor, explain ways to improve LPD. Now let us discuss the calculation of voltage regulation. This formula calculates the voltage regulation. Voltage regulation is equal to 1.06 into P into L into PF divided by LDF into RC into DF, where P is the total power in kVA, L is the total length of line from power sending to power receiving in kilometers, PF is the power factor in per unit, RC is the regulation constant kVA minus km per 1% drop, LDF is the load distribution factor where LDF is equal to 1 to 2 if load is skewed towards the tail end of the feeder, LDF is equal to 2 for uniformly distributed load on feeder, LDF is greater than 2 if load is skewed towards the power transformer. DF is the diversity factor in per unit. Let's learn more about the diversity factor. The diversity factor is the ratio of sum of the individual maximum demands of the various subdivisions of a system to the maximum demand of the whole system. Diversity factor DF is equal to summation of individual maximum demands divided by maximum demand of the system. By substituting values from the figure and simplifying, we get DF as 3.07. Loads do not normally all peak at the same time. The sum of the individual peak loads will therefore inevitably be greater than the peak load of the composite system. The diversity factor normally has a value greater than unity and is only equal to unity if all the individual demands occur simultaneously. The coincident nature of load demands is of great importance to the distribution planning engineer as it is a key factor in the economic sizing of plant. Figure shows the effects of coincidental and non-coincidental demands. Let's understand why voltage regulation is important. When characteristics of lamp loads, that is lighting, are considered, as they are very sensitive, fluctuation in voltages are immediately reflected on the intensity of the lux level. When power loads, that is motors inductive, are considered, the voltage variation may create erratic operation of the equipment. Greater the variation in voltages will generate excessive heat on distribution transformers. All the above can be avoided by having effective regulation. The table illustrates data regarding maximum voltage regulation from three different parts of the distribution system. Up to transformer, in urban area it is 0.5%, in suburban area it is 2.5%, and in rural area it is 2.5%. Up to secondary main, in urban area it is 3%, in suburban area it is 2%, and in rural area it is 0%. Up to service point, in urban area it is 0.5%, in suburban area it is 0.5%, and in rural area it is 0.5%. In total, in urban area it is 6%, in suburban area it is 5%, and in rural area it is 3%. Let's discuss the methods adopted to bring voltage regulation within permissible limits, which are as follows. On the primary side, the load balancing can be carried out. By reconductoring, the size of the conductor can be increased. If the feeder section is of single phase, then it can be changed to three-phase. A new substation or primary feeders can be introduced. Loads of existing can be transferred to newly introduced feeders. Introducing series condensers is another solution, and introducing voltage regulating equipment is another solution. Let's understand the definition of following terms. Power factor, active power P, reactive power Q, and apparent power S. In an AC electrical installation or an equipment, power factor PF is expressed as the ratio between the true or actual power measured in kilowatts to the apparent power consumed in kVA. PF is equal to kW divided by kVA. Active power P is expressed as the true power or actual power required for performing a task like providing illumination, water pumping, heating water, etc. The unit of measurement is W watt or kW kilowatt. The reactive power Q is expressed as the reflected on source's stored energy does not perform any useful task. The unit of measurement is VAR or kVAR. The apparent power S. If we add vectorially the active power and reactive power, we will get the apparent power. The unit of measurement is VA or kVA. When we need an efficient system serving heavy loads, it is always preferable to have the power factor as close to unity as possible. Let's look at reasons for low power factor and ways to improve it. The poor power factor may be due to inductive loads such as induction motors, transformers, inductive furnace, etc. The loads like rectifiers or inverters are used will have a distorted current waveform which may also cause lower power factor. Now let's discuss the ways to improve LPF. In a system having poor power factor, improvement can be achieved by deploying power factor correcting equipments or capacitor banks or synchronous motors on the load side as per the system requirements. Poor power factor caused by this type of current waveforms needs a change in design or harmonic filters are to be added to the circuit so that the power factor can be improved. Let's understand why the power factor needs to be improved. The power factor needs to be improved for the following reasons: to improve the energy efficiency, to reduce the energy charges, to enable availability of extra kVA from the existing source, to enable reduction of transformer losses, to enable reduction of distribution losses, extended equipment life. Let's discuss the effect of power factor compensation. The figure depicts how power factor is getting improved after introducing power factor compensation equipment. From the figure 1, we can understand that the system is having a much lagging power factor, PF lag, as indicated by a vector in the yellow portion. During this period, let us remember that the system is having a major inductive loads. This requires improvement. Accordingly, power factor improving equipment like condensers or synchronous motor or harmonic filters have been introduced. Now let us refer figure 2, wherein the latest power factor is described. As you can see in the yellow portion, the vector of lagging power factor is indicated, and in the pink portion, the power factor PF lead due to the introduction of power factor improving equipment. When vectorially added, we are getting the resultant power factor PF res, which is much improved from PF lag. Let's discuss the effect of power factor improvement. Power factor can be improved by adding power factor correction capacitors to the distribution system. The figure depicts the picture of power triangle. It exhibits the status of the systems earlier to addition of capacitor, triangle ABC, and after addition of capacitor, triangle ABD. It will be evident from the triangle ABC that before addition of capacitor in the system, power factor is equal to 0.70 lag, apparent power required is equal to 142 kVA, to generate active power is equal to 100 kilowatts. It will be evident from the triangle ABD that after addition of capacitors 67 kVAR in the system, power factor is equal to 0.95 lag, apparent power required is equal to 105 kVA. To generate active power is equal to 100 kilowatts. This shows that there is a reduction of 35% in apparent power in kVA. In distribution system, power factor can be improved by adding PF correction capacitors. Let's discuss the methods of power factor correction. Different methods of power factor corrections are shown for the information. Let's start with diagram 1 and follow the clockwise direction. Diagram 1 shows capacitors connected before thermal element of the relay in the starter of the motor. Diagram 2 shows capacitor connected after thermal element of the relay in the starter of the motor. Diagram 3 shows capacitor connected in the same bus in which the motor is connected with independent isolation facility, and group power factor correction is done as shown in the figure, and centralized power factor connection is done as shown in the figure, and sample of automatic power correction panel is shown for your information.